My name is Brian Musisi.
Okay, so we're now going to look at convolutional neural networks in code in Python. And so we're going to see how we can create convolutional neural networks, and we're going to compare with what we saw earlier on with the basic neural networks and see how these can provide an improvement in terms of accuracy. So we're still going to work on the same image classification task, and we're going to use the MNIST dataset. And so we're going to first run our same imports, and so this is basically, again, just fetching the data from the open dataset. And so that's done running. So this is similar to the task before, basically just shuffling our data and creating this time we're going to use 30,000 train examples. Before we used 5,000, but now we want to increase the size of the data. And so we run that. And so, yeah, so now we can actually start to create our convolutional neural network model. And so we're going to we use the same sequential API. And so in this case, we're just basically going to be adding layer after layer. And so the first layer that we're going to add is a convolutional 2D layer with the acceleration layer as ReLU. And this basically helps us initialize our kernel. And if you remember from what we had before, the MNIST dataset is 28 by 28. And so we're going to change this to a 28 by 28 by 1. Because this is expecting 3 different layers, and the 1 is basically for depth. But in this case, all our images, we don't have the RGB values, so our depth is going to be 1. And so we're going to add a 2 by 2 max pooling layer, like that, and we should know what that is now. And then we're going to flatten this before we pass it on to a dense layer. And so flattening is basically turning this 2D, 3D layer into a one-dimensional array, sorry. And so when we pass this, we're going to pass this to a dense layer of size 100 and another dense layer of size 10. And so this uses the ReLU activation, or this last one is using softmax as the activation. And softmax, like we've seen before, is basically going to transform these probabilities and normalize them for us. And the optimizer we're going to use is SGD, which is stochastic gradient descent. And so we can now compile our model, and the metrics we want is to look at is accuracy, and the loss we're going to use is the categorical cross entropy. So we could run this now, and we can look at the summary of our model, and this will just show you what the model is at the different layers. And one interesting thing you can see here the number of parameters that you have, and all of them are trainable here. So we have over 500,000 parameters. And so we're also going to convert our outcomes to integers, like we did before, because that's what TensorFlow expects. And so we're going to preprocess our data here just quickly. So we're going to, if you look at the shape of the X train, which is the training data, is 30,000 by 784. So before we transform this, we're able to visualize this with 28 as a 28 by 28. But we are now going to change it into a 28 by 28 by 1. And so if you look at this shape, we can see it's 28 by 28 by 1. And so we're going to also convert the test data as well, and we can look at the shape of just the first and see it's also 28 by 28 by 1. So this will allow us to feed it into our model here, which expects the input shape to be 28 by 28 by 1. So again, we can view the data and just see, we can see the first example is a 1, and even the data shows it to be a 1. And here the 35th example is a 5, and the data shows it to be a 5. So we can start to train our model here. And this model, in this case, expects our variables to be in a binary sort of manner. So we're going to change this to categorical, which we're going to use the function called toCategorical. And we saw before, scikit-learn has a similar function called label binarizer, but also TensorFlow has its own version called toCategorical, and we can use that. And we could just see what this becomes in the end. And so you can see it's sort of it's a one-hot encoding, just like we saw with label binarizer. And so we'd expect this value in y train 0 to have been this would correspond to a 1. So because position 1 has basically 1, and we already saw that before when we run y train 0 here. It had a 1 before, but then when we run the two-categorical one-hot encoding function, it has now turned it into this, where position 1 has a 1, while position 0 has 0, and all the other positions have 0s as well. So another thing we can do, we can sort of divide this by 255, and this is going to sort of reduce the size of the model and create values that are between 0 and 1. So not reduce the size of the model, but reduce the size of the figures. So before we had from 0 to 255, but by dividing by 255, we're going to have values from 0 up to 1. And that could make it easier in terms of the range of values that we're working with. And so we're now ready to feed in our data. So we're going to train the model. And this time, since we're working with 30,000 examples, it may take a little bit longer, and we've asked it to run 10 epochs. And so we'll just wait for this to run. So right, this has finally finished training, and so we can evaluate it on the trained data and on the test data now. So if you remember last time, our best accuracy was 93%, but now with our first version of the convolutional neural network, we can see on the trained data, our best score is 99.9%, which is basically 100%. While if we look at the test data, our best before was 93%, but now we've jumped all the way to 98%. And this is just with the first version of our convolutional neural network. And so we can already see that the convolutional neural networks, because of their ability to understand images and positions and how the convolutions are able to understand, regardless of where an image is, where a particular digit is in the image, just being able to understand what that image could be, we can say that we already have improvements in those. So we're now going to work with even more convolution layers. So we're going to add 2 more convolution layers. And so before we had, if you see the conv2D layer here with a size of 32, and we're going to now add 2 more layers here, and with max pooling in the first 2 layers as well. And so we are going to run this to create the model and then feed on it. And so this time we are having it run with 10 epochs. And so we'll just wait for this to run and then see the value as well. All right, so this has finished running, and just maybe you may be wondering why we have this validation data attribute here. And so if you see, there's a column here called val loss, and so what this is doing is that it's running the loss on the validation data as well. So this is on trained data, and the accuracy here is on trained data, and then it's running the validation on the test data and giving you this loss here. And so you can see how this changes. And then in addition, it's also running the validation on the accuracy on the validation data here and giving you this accuracy here. So ideally, you would want to have 3 sets of data: your train, your validation data, and your test data, so that what you pass here is actually the validation data, and then you don't have to use your test data until the very end when you're evaluating your model. So what we can see now here, if we look below, we can see on our test data is giving us an accuracy of 100%, while on the test data it has increased a little bit and has now moved to about 98.5, or very close to 99%. So we are basically almost with certainty able to classify what particular image it is based on the pictures that we get. So one thing to note here, you may see that you may notice that the accuracy here keeps increasing as we expect, but then after a while here it does a little drop, but then basically the last 1, 2, 3, 4, 5 epochs, the accuracy is not changing. And so we could have stopped at this point here and still have had a very good accuracy. And even if we look at the validation accuracy as well, we can see here it's basically not changing in the end. So one technique that we can use is a technique called early stopping. And so what early stopping allows us to do is to basically stop much earlier as soon as the accuracy stops improving. So TensorFlow has something called callbacks, and we can use a callback called the early stopping callback, and we're going to ask it to monitor the validation loss. And so what it's going to do is that as soon as the validation loss stops improving, which in this case stops decreasing, it is going to stop running the model and give us a result at that point. And what the patient sees is basically when it stops decreasing, it's going to wait 3 epochs in this case, and then after running those 3 epochs, if there's no improvement in the validation loss, it's going to stop. So I'm just going to reduce this to 1 so that as soon as the next epoch doesn't improve the validation loss, it will stop running. So let me just run this just to make sense. So we're going to fit our model, and in this case, we're going to pass a list called into the callbacks parameter here. And if we just run this now and fit, we should expect that at this point it shouldn't go through all the 10 epochs in case the validation accuracy stops increasing. And again, we've given it a patience of 1. So as soon as it finds no improvement after 1 epoch, then it will stop. But we could increase this to as much as we want, 2, 3, 4, or even higher, depending on how many epochs you're running. So let's wait for this to run now. Right, so this has completed running. So what you see here is that we specified 10 epochs, but before it even got to the 10th epoch, it stopped running, because if we look at the validation loss here, which is what we asked the callback to monitor, is that it keeps decreasing here, but you see on this next epoch, it comes from 0.0468 and increasing slightly to 0.0471. Because our patience is 1, basically we're only willing to wait for 1 epoch to see if there's an improvement. As soon as it increases here, in the next epoch, it stops. And so this allows us to basically save time and not overfit. And again, we can see here the accuracy is still as high as before, and it's actually just slightly higher because it's probably not overfitting as much. And so this is basically 98.7, close to 99% on the test data. And we can see, if we look at the trained data, here on the trained data, we saw it got up to 100%, but that was likely because it was overfitting. Here we saw it only goes up to about 93, 94% on the trained data, and basically it doesn't overfit and allows our model to generalize even better. So we have basically come from a point where we had our best accuracy being 93%, and if you go back much earlier to when we had logistic regression, it was about 82%, and now with convolutional neural networks, we've gotten to a point where our accuracy is even 98.7%, which is a much bigger improvement from what we had before. And so this is helps us understand what these different neural network architectures can help us handle different tasks, in this case, in particular, image classification. So yeah, that's it for neural networks and convolutional neural networks, and I encourage you to go and explore even more the different architectures like the LSTMs and the RNNs, and better understand these important parts of machine learning. Thank you.